The first step for our physics cart lab was setting up the track. You can see in the back there are 2 poles placed, and that will be our scale. The scale is 0.5 meters long, so that way we will be able to measure how far the cart goes. As seen from the video on our last slide, we were able to plot points as the cart moved up and then down the incline. As the cart moves up the track, we plotted points to find the car's acceleration in the upward direction. As the cart moved back down the incline, we were able to plot the points to find the car's acceleration in the downward direction. After we made the points as the car went up and down the incline, we were able to plot a position versus time graph. As seen in this graph, the graph is a parabola, and in the middle is when the cart reached the top of the incline. We set our origin so at the lowest point is when t equals 0. Based on this graph, we were able to find the acceleration with a certain percentage of uncertainty. That was less than 5%. The next step is calculating theta. We did this by first using our scale, which was 0.5 meters or 50 centimeters, and had that as our hypotenuse. We then were able to measure using that scale the leg of the triangle, which was 2.4 centimeters. From there, we were able to use the inverse sine function to find what theta equals. As seen, the inverse sine equals 2.4 centimeters divided by 50 centimeters, which will give us a theta of 2.751 degrees. As mentioned in a previous slide, the parabola that was calculated using the software was then matched to a curve, giving us our upper and lower bounds with varying resolutions to calculate the acceleration within a 5% uncertainty. From the first picture, we can see that we had a range from 0.2618 meters per second squared and to 0.2418 meters per second squared. By adding them together and dividing by 2, we were able to get an average of 0.2518 meters per second squared as our acceleration as the cart moved up the track. We're then able to calculate a 4% uncertainty for our upward acceleration. For the bottom picture, we can see that we had a range from 0.2261 meters per second squared and 0.2161 meters per second squared. As we add those two together and divide by 2, we have an average for our acceleration downward of 0.221 meters per second squared. Using our two numbers we added together, we can calculate that we had a 2.26% uncertainty for our acceleration in the downward direction. These are the free body diagrams for the cart as the cart goes up the track and as the cart goes down. You will notice that the normal force is the same for both of the free body diagrams and the weight is the same. The only difference is the direction friction is pointing in. As seen from the force body diagrams, we are able to make some of the forces for X and Y as the cart goes up and down the track. First, we will calculate for the sum of the forces in X and Y as the cart moves up the track. As we can see from the first picture and the top left, sum of the forces equals MAX as the cart goes up. This means that the friction force plus W sine of theta equals MAX as it goes up. Friction equals mu times N, so we sub that in, and we'll get mu N plus W sine of theta equals MAX as the car goes up. We can get the normal force from the sum in the y direction. As we can see, the acceleration in the y as the cart goes up goes to 0. So our normal force will be equal to W cosine of theta, where W is just mg. So normal equals mg cosine of theta. We can sub that back into our sum of the forces in the x direction, and we'll get mu mg cosine theta plus mg sine theta equals maxu. Each of the terms has an m in it, so we can cancel that out to get our final equation for the sum in the x direction as the cart goes up the track as mu g cosine theta plus g sine theta equals ax up. The next step is finding the sum of the forces as the cart goes down the track. So, as we can see from our force body diagram, for the sum in the x direction, W sine of theta minus the friction force equals max down. W equals mg, so now we have mg sine theta minus mu n equals ma dx. Again, we can go find the normal force from the sum in the y direction. So the normal force will be equal to W cosine of theta, which equals mg cosine of theta. We can sub this back into our sum of the forces in the x direction to get mg sine theta minus mu mg cosine theta equals max down. Each of the terms has an m again, so we can cancel those m's to get our final equation as g sine of theta minus mu g cosine theta equals ax down. We can use each of our final terms for the acceleration down and the acceleration up, and we can add those together to get mu. I will talk about this in the next slide. Now, as our final step for finding the coefficient of static friction, we take our two final equations for acceleration, where the acceleration in the up direction is mu g cosine of theta plus g sine of theta, and the acceleration in downward direction is negative mu g cosine theta plus g sine theta. And we can add these two equations together to get one equation of ax in the up direction minus ax in the down direction equals 2 mu g cosine of theta. We can rearrange this so it will equal mu will equal ax in the up direction minus ax in the down direction divided by 2g cosine of theta. By plugging in our accelerations for x of up and x of down, g where equals 9.81 meters per second squared, and theta, which we found earlier, which was 2.751 degrees, we get mu equals 0.00157.